currently I am working on analysis of, this is a topic of my presentation, analysis of multi-cell lithium-ion configurations with dissimilar SOC for battery swap application. And currently in my project, I am working under the cell equalization using a particular converter topology. So this will be the outline of my presentation. First, I will address the problem, then what are the state-of-the-art techniques prevalent, then various multi-cell configurations, their analysis, and behavior analysis of two-cell models and four-cell models. So coming to the problem statement, as we know that the battery energy systems are very prevalent in today's time, and there are different chemistries of battery that are present, but amongst them lithium ion has advantages compared to other chemistries because of its lower weight and higher charge density. Also, the battery applications, we need to connect them in, the cells needs to be connected in series and parallel to meet the voltage and current requirement respectively. However, there may be chances when in a particular battery, the cells that are present, they have different state of charge levels at a given time. So this will impact the battery characteristics and performance. Like in the figure 1, as we can see that at a given time, let's say these are the charge levels that are present in different cells of the battery. Now, if this battery is charged, then the cell with the highest charge will get charged at the fastest, and if there is any battery management system is present, then it will cut the charging circuit, and these portions will remain uncharged, and this will be the wasted capacity. Similarly, if this particular configuration is discharged, then the cell with the lowest charge, it will be discharged quickly, and if any battery management system is present, it will cut off the circuit. At that time, other cells are having some charge which will be wasted. So this is one of the problems when the cells having different charge levels are connected in a battery. Now coming to the state of the art, in my work, I use the runtime based cell model for the simulation purpose. In this type of cell model, the entire cell model is modeled using a dependent voltage source, which are connected with series and parallel RC elements. So one particular characteristic of this cell model is that here the open circuit voltage, the resistors and capacitors, they all are expressed in terms of the state of charge that is present. So in every iteration, all the parameters are updated. As I mentioned in the state of charge, it is a very important parameter in case of batteries, which represent the capacity of the cell to supply energy to the connected load. So the state of charge is updated in each equation using the equation, in each iteration using the equation 1. Here IBAT is the discharge current and CFD is the capacity of the battery. In the figure 3, I have simulated a particular cell open circuit voltage versus SOC characteristic. Now coming to another thing, that is battery swap charging scheme, which is prevalent nowadays. So it is usually the mechanism for charging the electric vehicle by replacing a discharged battery with a pre-charged one. So it is very much popular because of advantages like you don't have to wait at the charging station for the battery to get charged, which is usually it takes 30 minutes to charge. So in this case, the battery only needs to be swapped, like the discharged battery is swapped with a charged battery. And also, if the battery swap charging is used, then while buying the electric vehicle, we don't have to buy the battery with the vehicle, hence the cost is also reduced. So using the data shown in reference 4, I have drawn this bar graph. Here I have shown the cost-based analysis of lead acid and lithium-ion based electric vehicles over a period of 5 years. So as we can see here that the lithium-ion cells are having, batteries are having a higher charge, higher cost over the entire period. This is one of the disadvantage considering, but there are other advantages as well, like the higher charge density and the lower weight. But here we can see that I have used battery swapping cost with lead acid battery, which is denoted as a black dot, and battery swapping cost with lithium ion battery, which I have denoted as asterisk. So over a period of 5 years, we can see that like the lithium ion based electric vehicle, which uses a battery swap scheme, it has the minimum cost compared to other cases in this comparison. So hence it has various advantages as compared to the conventional electric vehicle with batteries. Now coming to my work, that is the analysis of multi-cell configuration. So I have used a typical lithium-ion cell having the values of nominal voltage 3.8, capacity 0.75 ampere. I am discharging it with a discharge current of at C rate, that is 0.75 ampere. Here, as I had mentioned earlier, the cell model that I am using having the open circuit voltage and all the resistor capacitor that are dependent upon the SOC values. So keeping the power like load requirement same, I have considered two cell model in which they are connected in series and other in parallel. Similarly, keeping the power demand same, the four cell model I have able to uh, connect them in three combinations. Now coming to the behavior analysis of two cell model. In the first case, I have considered two cells connected in series which are discharged at a constant current source of 0.75 ampere, that is at 1 C rate. So when both the cells have the state of charge same, that's 100%, or the open circuit voltage and everything are identical. Now coming to other case, when I have taken the cell 1 is 100% charged and cell 2 at 0.75, that is 75%. We can see here that there is a variation in the open circuit voltage, as our open circuit voltage is a function of SOC. But eventually at around 300 second, we can see that the cell with the lower SOC getting discharged to the minimum voltage level, whereas the other cell at 100% is still charged. So in this condition, we have two problems. One is that one cell is getting into deep discharge, while the other cell, the capacity is getting wasted. So the other case which I simulated is one is at 100%, other I have decreased further to 50%. The same thing we can observe here, even the cell, one cell is getting discharged very quickly. So this creates a very hazardous situation in case of the health of lithium ion cells. Now coming to the parallel connection, I have connected both in parallel and discharged with 1.5 ampere hour. So when both are at 100%, the characteristics are same. However, when I have considered one cell at 100% as a 75%, we can see that initially the open circuit voltage are according to the SOC variation, but at around 1200 second they are same. This happens because as the terminal voltage needs to be maintained, there is some current flowing. The loading of the cells will vary, so to maintain the terminal voltage across both the cells same. So this phenomenon is known as the intercell balancing. Now when I decrease the SOC further, like one is 100%, other is 50%, we can see that the loading of the cell one is further increased just to maintain the terminal voltage same. Now I have considered four cell models. Here I have considered different values of the SOC, like cell 198, cell 275, cell 395, and cell 450. So here what happens is that like in string 1, cell 1 and 3 are connected in series, and string 2, cell 2 and 4 are connected. So the loading will be dependent upon the equivalent SOC of both the cells in a particular string. Like here we can see that cell 1 and 3, they have a higher SOC compared to the combination of cell 2 and 4. So the current from this string will be higher than that string, just to maintain the terminal voltage across the cells similar. As you can see here in the current in the cells, the loading is according to that. The same combination when I discharge at 0.5 C rate, the behavior of the currents and voltages are same. Only the time taken to reach the value is a little longer as it is discharged at a lower rate. Now I have considered another combination using a four cell combination. This is different from the other before combination, as 1 and 2 are connected in parallel, which are further connected and 4. So here what I have taken the same values of SOC as in the previous case. So here what happens is there will be intercell balancing current in this network, and similarly in this network to maintain the voltage, terminal voltage of the cell 1 and 2 same, similarly cell 3 and 4 same. So coming to this network where cell 1 and 2 are connected, so as cell 1 is greater than cell 2 charge, and cell 1 will be more loaded than cell 2. Here we can see from the currents, so as to maintain the terminal voltage same. Similarly, in cell 3 and 4, here as 3 is higher than 4, the charge level, so 3 will be loaded at a higher current than cell 4. And the same thing I have discharged using 0.5 C rate, and the same behavior is observed. So I would like to conclude by drawing the inference of what I have conducted in my work is that in series connected cells, when there are dissimilar SOC, there are two major problems. One is obviously the net terminal voltage is lower, and other is
There is a chance of the cell having a lower charge level to get into a deep discharge, which is a hazardous situation in case of the lithium-ion cells. Whereas in parallel connected cells, when dissimilar cells are connected, there are intercell balancing current prevalent, but these currents also needs to be controlled. Otherwise, it will hamper the life of the battery. Also, if we use this particular combinations in electric vehicle batteries, they play a role in deciding its mileage because of the same intercell balancing currents. So this work has been published in ICPEE paper, conference paper, and thank you.